This lesson is going to focus on how to find zeros for polynomials, on how to solve them, their roots, the solutions, where they hit the x-axis, and some things that you need to know. You should have copied from class. The sum of cubes, this is also on Canvas. You need to know the sum of cubes formula, the difference of cubes, these things you should have seen before, and of course the quadratic formula, because you will be using these things in solving some of today's problems. The other thing that you should have copied were some strategies for factoring and solving for zeros. Number one thing is always look for a GCF to make sure that there's nothing that can be factored out. And then look at the remaining number of terms if you're able to factor out a GCF. If not, you still look at the term. So if there's only 2 terms in your problem, then think to yourself, is this a difference of squares, a difference of cubes, a sum of cubes, or can I just solve it straight out? Sometimes even with the difference of cubes, you can do that, depending on what it is, and you'll see those examples. If there are 3 terms, we think about a trinomial. Is it a special product kind of situation? Is it a traditional method, like, box method, things of that nature? You can think of quadratic formula as well. So you have to think about those. Which ones can I use to solve it? A lot of times when you factor out, or you're able to pull something out like difference of squares or difference of cubes, more likely, or sum of cubes, you'll have a binomial and then a trinomial, and then you'll have to end up using quadratic formula because a trinomial will not be factorable. If you have 4 terms, you need to think about factor by grouping, and that's where you have to look to see, can I group them together and find out if they have similar binomials that can come out, and you look at that about the ratios, and we'll look at one of those in our examples as well. Or you can use a known rational root and use synthetic division to find the other ones, or to be able to factor down to a trinomial. If you do not know a root, you can also use the rational root theorem to help you find some possible roots. Or if you have Desmos or TA83 or 84, you can put the equation in, the polynomial, and have the calculator Desmos help you find a possible real root. Now, remember, you always look at the degrees. The number of degrees tell you the number of roots. That's the fundamental theorem of algebra. So if you put a degree of 4 into Desmos and you only see 1 root, do not just say it has 1 root. You should know it has 4, so that means the other ones are going to be imaginary or complex numbers. So they will not show up on your Desmos. Remember, the conjugate zeros theorem it says that if you have an imaginary or a root as an answer, you must have the conjugate as well. So we write those separately in our statements. So with our notes today, we went over a couple of things. Make sure you have your formulas written here because we refer back to these. And we're going to talk about a couple of these. But number 1, if we look at it first, we see a degree of 3. And so we know we're going to have 3 roots. And we're going to have to look to see how we solve it. We have 2 terms, so we got to think, how can we solve that? Is this a difference of squares or a difference of cubes? We see the subtraction, so we know it's difference, or can we just solve it? Well, with this one, this is a difference of cubes, and we could think about using our formula that we have up top. So with the difference of cubes, you take the a value, which in this case is our x, and then the cube of 64, which is 4. And there's also on Canvas a list of perfect squares and perfect cubes. If you don't know them, that might be a good thing for you to practice. And then we take the a and square it. And then the middle term is the a times b with a plus, so plus 4x. And then we square the last term. So a negative 4 and a negative 4 gives us a positive 16. So we can see this first term, we can actually set equal to 0, and that would mean x equals 4. And this other term here is not factorable, so we have to use quadratic formula to factor. Okay, so you go through the steps there of doing the factoring to find its pieces. Now, I'm going to skip a little bit and show you kind of once I plug it in what would happen as far as a quadratic, just to refresh your memory on how to break apart a negative inside of a square root symbol. But we also could have looked at this another way. We could have thought about it as a way to just solve it from the get-go. So if I had x to the third minus 64 and I move the 64 over to the other side, then I could take the cube root of both sides and I would have had x equals 4 as well. Now, if I would have done that, I'm still needing my two other roots, no different than I do here. If I started this way, I then could use synthetic division. So I'd put in 4, and then I'd have to put in 1. I don't have an x squared, so I put in a 0. I don't have an x, so I put in a 0, and then the negative 64. And I would use my synthetic. So if we do that really quickly, and then 64, and it should equal 0 because we know that it actually is a solution. And we started with a third degree, so this is second, so x squared plus 4x plus 16. And you see that this trinomial and the one that we did with the difference of perfect cubes are the exact same. We still have to use the quadratic formula from this point forward. So I plugged my information into my quadratic formula, and a little piece got missing there. And you see when I plugged it in, I get a -4 plus or minus the square root of a -48. So to help you break down this piece, think about perfect squares in there. We know that a negative inside a radical is the same as a -1. So I think about what makes 48. Well, 16 times 3 will get you 48, and 16 is a perfect square. So this is the same thing as saying the square root of 16 times the square root of 3 times the square root of -1, and then I can take the perfect square of 16, which is 4. The square root of -1 is I, and then the square root of 3 has to stay. So I can then reduce it down to a -4 plus or minus 4i square root of 3 divided by 2. Now that 2 can go into the 4, -4, and it can go into the 4i and make it simpler. So when we look at that, we get a -2 plus or minus 2i square root of 3. So make sure you simplify all the way down when you're dealing with quadratics. Okay, then you would write them individually. All three of your roots should be written individually, and you'll see that on the partial key that's listed, and then on the full key for the notes. Now, if we look at number 2, we have some roots there, 3 roots because it's 3 degrees. And the first thing I ask yourself, is there a GCF? So if we pull out a GCF, which there is, we could pull out 8, and we would end up with x cubed plus 125 when we did the division. Now I want to show this to you on Desmos, because if I put this in Desmos the way it is, and I show you, I only have, and I even zoom out there, this is just one root showing up, and it's at -5, okay? So I know there's one root at -5, but there's actually 3 roots, and notice that Desmos does not show them, because that should tell us that the other 2 are going to be imaginary or complex numbers. So we need to then use some type of strategy. Now we could have used factoring out, and then we've got a sum of perfect cubes, and we could use that formula, or we could use synthetic division from here, knowing that -5 is a root. It's up to you to do so. And then see where you go from there. 3 is a problem that has 4 terms. So 4 terms tells us, we either need to factor by grouping, or we need to use the rational root theorem to find some possibilities to help us then break it apart. So we're going to look at this one in 2 different ways. So we always want to look to see if there's a GCF, and there's nothing that can come out of all these pieces. And if we think about, could we use factor by grouping, and that should be one of your first things to think about. If you look at the terms, and you can rearrange the terms any way you want, but if you look at the terms, and you see here, this is a 1, and this is a 3, and then a 9 and a 27. Think about the ratio of these terms. So 1 to 3 and 9 to 27. Well, 9 to 27 also reduces down 1 to 3. So because they have the same ratio, then we know it's a good option to do with factor by grouping as well. So I'm going to show you 2 different ways here on this one, because I think it's important to see. So if we think about using our rational root theorem, that's where we take the constant, so our -27, and our leading coefficient 1, and we find all of the possible factors of that. So we can have plus or minus. So we have a 1, okay, 3, a 9, and a 27, and then this one's just 1. So our options for possibilities are 1, 3, 9, and 7. So if we pick 1, plug it in, see if it equals 0. If it does, then great. If it does not, then you move to the next one. will tell you that 1 does not work. So 3, I plugged it in, and 3 does work. So once I know that 3 is a root, and of course we could plug this into Desmos as well and see that 3 is a root, but we still know that we have to have 3 roots, so it would show up as just 1, not 3. So if we know that it is a root, we can then use synthetic division. We have 1, negative 3, 9, and negative 27. We bring down that first term, and we do our multiplying. Now, when we have this completely done, we should have a remainder of 0 because we know that this truly is a root. So when we rewrite this, this will be x squared. We don't need to write the 0x, so plus 9. And so that would be another factor. The factor that we found, the 3, if we write that as a factor, that's x minus 3. So if we write this one, this is x squared plus 9. And then we would have to solve both of those. And so x squared plus 9 would have to go a little bit further into solving because it's going to get to an imaginary number. Now, so notice that I had these pieces, these factors, when I use synthetic, and then I still would have to solve. But if I do factor by grouping, which some of you are still having a problem with, I want to go through that process. So we kind of break it up and we look at each section. So we look at what can we take out of this section. We can take out an x squared, and we're left with x minus 3. And here, what our goal is once we factor out something in 9x and negative 27, we want it to be the same binomial as x minus 3. So we can actually factor out a 9, and we get x minus 3. So those two are the same, so they get to come together. And then what we factored out gets put together in the other binomial. Okay, so from there we can solve this one. We know it's x equals 3, which we had solved already with using the rational root theorem. And now we can solve this one. So this x squared plus 9 equals 0. We can use our, this is a sum and this is squares, and we can't do sum of squares. We don't have a sum of squares way to do that. So we can move this 9 over. And we have x squared equals negative 9, and then to undo a square root, or a square, we take a square root. So we have x equals plus or minus the square root of negative 9. Well, we know that's the same thing as saying the square root of negative 1 times the square root of 9, plus or minus. And we have negative 1 comes out as an I, and 9 is a perfect square, so 3i plus or minus. So our answer would actually be x equals our 3 that we found earlier, and x equals 3i, and x equals negative 3i. Notice 3i and negative 3i are conjugates of each other, so we got to have them as a pair. All right, with number 4, always think about what type of degrees you're going to have, how many roots you're going to have, and then if you can pull out a GCF. You could use pull on GCF and then factor from there, or you can use Desmos to see do you have a known root and use synthetic division to get your trinomial and your binomial broken down. But factoring out a GCF first is very helpful. That might help you find a root to use. Now, sometimes when you factor out, you only see one root really easily, and then other times you might have 2 that you see easily, and then you have to find the other unknown 2 when it's a degree of 4. All right, you are going to be working on 5 and 6 on your own. I want to look at number 9 together. So number 9 says, find all the zeros for this particular one if the graph bounces at 1, 0. And if we talk about bouncing, it's actually hitting there twice. That means we have a no remainder twice. So if we think about this, we can look and see, could we factor by grouping? Well, look how many terms we have. 1, 2, 3, 4, 5. We cannot factor by grouping. So we're going to have to do something else. So that's where division is going to come into play. Now, we have a bounce at 1. So that's saying x is 1 twice. So x is 1 and x is 1. And we're going to write that way. That's 2 roots it's taken care of. If you put this into your Desmos, you're going to see it look like a parabola, but it's going to be a flatter looking parabola because it's to the 4th power. But we do have 4 roots, So we've got to find all 4. We have 2 of them. So then we would use synthetic division. Now, synthetic division, when we have a bounce, we're actually going to do it twice. So we're going to put in our pieces that we have, bring down our leading coefficient, and then we're going to work this really quickly. All right, so now we have our new, we started at 4, so this would be the third, so x to the third minus x squared plus 9x minus 9. Now, this is still to the third. We have 4 terms now. We could factor by grouping if we wanted, but that would be unnecessary extra work, but you could. We're going to go ahead and use 1 again because this bounces at 1, so that means 1 is our solution twice. So we're going to do the same thing, but this time we're going to use this new equation that we created. Now it's pretty easy because we can just use what's already down here in this final row for our numbers. So 1, negative 1, 9, and negative 9. And we're doing the same thing again. So we have 1, 0, 0, 9, and 9, and 0. So now what we have is we started with the third this time, so this is going to be the second, so x squared plus 9. And we've seen this one before somewhere, so you should be able to solve this part and then find your other 2 roots. Now, with the final one I'm going to talk about is number 10. We're finding all the zeros starting with the rational root theorem. So we have something to the third power, and that is going to give us 3 roots. Now, when we have 3 terms, you can think about special products or just traditional methods of, factoring. Now, traditional method meaning that you would, factor x and x, and you would think of 7 and 1. Well, I got to have a negative here, and I can have a positive here to figure it out. So if I have to have 1 to be negative and this has to be positive, 7x and a negative 1, but this is a third. This is not a squared. So we can't do that traditional method because it is cubed. So it's got a term in the middle. So we are going to use the rational root theorem because they didn't give us any idea of what a possible root is, where the previous ones did. So we're going to look at p. Our p is our negative 7 over q, which is 1. So our possible factors, plus or minus 1 and 7. So those are our possible roots. We could put this into Desmos and see as well, but for this one, I need to see your rational root theorem happening. So I'm going to plug in 1, so f of 1, plug into the problem, 1 cubed plus 6 times 1 minus 7, and then it should equal 0. If it does not equal 0, then 1 does not work. Now, negative 1 might work, or 7 or negative 7 might work, but we're going to see if 1 works first. Always the easiest way to go. So 1 plus 6 minus 7, well, that's 7 minus 7, which does equal 0, so yes, it does work. So x equals 1 is one of our solutions, one of our roots. So now we can use the synthetic division. So we're going to go ahead and put in our 1 in the box. We had a 1 for the third. We do not have a second, so we have to put a 0 for that holder. And then a 6 and a negative 7. Bring down your first term. We have a 1. 1 times 1 is 1. Add them together. 1 times 1 is 1. Add them together. 7 times 1 is 7. Add them together. And you should have no remainder because we found out 1 is a solution. This started out as a third, so this is x squared plus x plus 7. Now, we could see if we could use traditional methods because this is a quadratic. However, this is not factorable, so we would have to use quadratic formula to then find our other 2 roots.